This video is, let me just make sure it's running. Yep. This is a video about covalent bonds. So ionic bonds are when electrons are transferred, when the metal usually loses, the nonmetal gains. Now we're talking about a covalent bond. Both types of bonds, ionic and covalent, happen because the atoms want to have an octet of electrons and they become more stable. So a covalent bond is the result of sharing electrons between two atoms. When you have that covalent bond, like these electrons here, getting shared in the middle, and they're attracted to both the nucleus of the one that they came from and the one that they are bonded with. So like one of those electrons would come from the left atom and the other electron would come from the right atom. A molecule is what you get when they're bonded covalently. They're distinct particles or molecules, different than an ionic where you have that crystal lattice. Diatomic molecules, these are elements that exist in pairs. So if they don't bond to something else, they'll covalently bond to themselves. So this is just showing you like two fluorines, how do they bond, and they're going to share their electrons between them. So then they each have an octet of electrons. We're not going to show it with that type of drawing. We're going to actually show it, and I'm going to teach you in the next lesson. We represent the single covalent bond as a line. And I know I'm going to be going over how to do these drawings. So a single covalent bond represented, it's one pair of electrons. So it's really two electrons being shared. Lewis structure is, like I was just showing you, when you do a line to represent that single covalent bond. So for this example, like the hydrogen bonded to the hydrogen, this would be another example of a Lewis structure. Sigma bonds is the same thing as a single bond. There's also pi bonds, but we're going to just talk about sigma really briefly. So this, like here, each of these bonds, those lines are sigma bonds, versus if I had, oxygen double bonded to itself, that's a non-example of a sigma bond. We do have doubles and triple bonds. So like I was just showing you with that oxygen, a double bond is going to be shown with two lines. In each line is two electrons. So really it's 4 electrons being shared between two atoms. So right here is an example of a double covalent bond. And then a triple covalent, and that's as far as we go. There's nothing past triple, is when there's, and we show that with 3 lines. So 6 electrons are being shared. So this is a triple bond. So if you look at this table here, as you're going from a single to a double to a triple, the bond length gets smaller as I go. And the bond dissociation energy is the energy that would be required to break the bond. That gets larger. So it's showing you like a triple bond is going to be shorter and it's going to have a higher bond dissociation energy, which really means it's it's more stable, because if it's hard to break the bond, it's going to most likely stay bonded. And then the definition here, so this is just talking about, as the length of the bond gets smaller, the strength increases. And it gives you the definition of bond dissociation energy. And then just in general, when you're forming, a compound, whether this is ionic or covalent, you start with the elements and their energy that they have. And then you end up with the compound. It'll have less energy. So all of this extra difference in energy is going to be given off into the surroundings, and that's called exothermic.